it's made the noise now. So I'm going to be starting in the webinar in 3, 2, 1, and we're broadcasting.
Hi everybody, welcome to this seminar, which is the third in our IBIPSA education webinars on urban building energy modelling. I'd like to welcome you and welcome Shyam, who's going to be speaking today. This seminar is going to be on the use of urban scale simulation in stock level retrofit decision making. And the seminar is part of the mission of the IBIPSA Education Committee, and the Education Committee exists to identify training and education needs throughout the building performance community, wherever you are based, to initiate and develop new education materials and methods and support that when others are doing that as well. And the sessions that we offer are open to members as well as to non-members. So the format of today's webinar is going to be slightly different to the last two that we had in this series, because I'd like to ask you some quick questions, a little bit of market research, so we can try and learn a little bit more about who is attending the webinars and how we can best serve that audience. So I'll ask you a couple of questions at the beginning, then Shyam will do his presentation and we'll take questions and answers at the end of that. You will have a little box in the toolbar for Q&A, so if you could please type your questions into that, and I will manage the questions and put them to Shyam, and then I'll have another couple of questions for you at the end. So I will move on to my first question, which is, which of the following do you think best describes the role in which you use building performance simulation? So are you a professional using building performance simulation? Are you a student learning about it? Or are you an academic? There's a Mentimeter code at the top of the screen, and if you could please use that. Thank you very much to our first adopter who's found the button and answered the question. And then if you can use that to let us know. It's really helpful for us to understand where people come from, what background they have, so that we can make sure that the sessions that we're offering are tailored as much as we can to you. So I'll give you another couple of minutes. I think we have 26 participants at the moment and 11 responses. So I'll give you another couple of minutes to reply to that. Okay, thank you very much to everybody who's let us know. That's a really interesting spread across those 3 different sectors. I have another question for you just now before we get started with the presentation, which is, where in the world are you based? That's great. Thank you very much. So with that, I will hand over to Shyam and ask you to start your presentation.
Thanks. I'll just share my slides. So hopefully now you can see the full screen slides. Just give me a nod, Pamela, if that's the case. Great. So yeah, I'm Shyam Amrith. I'm a PhD student at the University College London Energy Institute. And as Pamela's already said, I'll be talking about using urban scale simulation for stock level retrofit decision making. And thanks everyone for joining the webinar today. And judging from the location responses, I should say good evening, good morning, and good afternoon to all of you. So I'll be talking a bit of background about the state of the stock and why we need retrofitting. Then talk a bit about what retrofitting actually is and how it can be done. I'll move on to urban building energy modeling, which is the topic of this webinar series, but specifically how these can be applied for retrofit analysis and some examples of how this has been done. I'll talk about why it's useful to apply optimization to models such as this and the justification for that, and then talk a little bit about the topic of my PhD research, which is how we can apply optimization at this building stock level and some of the challenges associated with doing that. And then I'll take a little bit of a broader view at the end and talk about the challenges with regards to applying UBEMs for retrofit analysis and a look to the future. And at any point, if you have any questions, just feel free to drop them in the Q&A box, as Pamela said at the start. Yeah, a bit of background on the state of the stock. So globally, buildings are responsible for roughly 40% of carbon emissions. And in Europe alone, it's estimated that 97% of buildings are not energy efficient. And most of these will still be standing and still be in use, in fact, in 2050. So there's definitely a real need to transform the way that our buildings use energy and to reduce the carbon intensity of our current stock. To add to this problem, though, local authorities have a limited budget and resources with which to address this problem. But before we get into that, just a quick summary of what retrofitting actually is. So Jafari and Valentine give this definition in that it is the physical or operational change in a building or its energy use equipment or its occupants' energy use behavior to convert the building to a lower energy consuming facility. And these are not obscure technologies. So these are approaches we've all heard of. This could be applying insulation to a building, either externally or internally to the walls and the roof. This could be upgrading the windows to a more efficient standard, for example, double or triple glazing in some instances, and having some low emissivity coating, which can either trap the heat in or trap it outside, depending on the climate the building located in. And this could be improving the airtightness of a building too. And all of these are fabric upgrades, which reduces the sensitivity of the internal condition of the building to the external weather and climate. We can also upgrade the heating and cooling systems to a more efficient model. So heat pumps are a promising technology for heating and cooling buildings, but this allows us to use less energy to achieve the same amount of heat. So we can upgrade these systems too, but we can also improve the equipment and the lighting within a building. And finally, we can consider renewable energy technology on site, and the most common of which being applying solar panels to the roofs and sometimes accompanying these with batteries to store the electricity that is generated on site. And the choice of retrofit depends on a number of factors, which we'll see slightly later. But there have been a number of observed benefits related to retrofitting as well. The most obvious being the energy savings, since we often call this an energy retrofit. And this is because, as I said, the internal condition is less sensitive to the external, but also the systems are more efficient in achieving this heating and cooling demand. This has associated with it a reduction in CO2 emissions, since you'll either be using less electricity from the grid or you'll be burning less fuel on site. But we also have health benefits, so we can see improved thermal comfort. And this is because the chances of overheating in summer can be reduced, but heat loss in winter can also be minimized. But also we can see some improved air quality when the retrofit is conducted in a correct manner. And this can lead to a lower amount of damp and mold inside, for example. Now, because retrofits can save energy, this also has the potential to reduce fuel poverty because occupants can spend less on their energy bills. And perhaps more difficult to measure directly, but still quoted by quite a few studies, is the associated job creation with the implementation and the retrofit market, and also the potential for greater energy security, since the vulnerabilities to fuel supply disruptions or price fluctuations can be minimized. Are we retrofitting enough? And the short answer is no. So the International Energy Agency estimates that the building sector is not on target currently to achieve net zero by 2050. And in order to do so, the sector's energy intensity must drop 5 times quicker this decade than it did between 2015 and 2020. So this will require an increase in the average retrofit rate from 1% a year to at least 2.5% a year by 2030. But the key thing to note here is that many of the technological solutions to building emissions already exist, as we've seen on one of the previous slides. That's not to say that innovation isn't happening in this area too. It is, but we do have the means to address this problem already. And the main challenge here is to roll out these technologies at sufficient speed and scale, and also to make informed and appropriate choices about how to treat our building stocks. According to a report done last year called the Global Retrofit Index, most countries' retrofit strategy is piecemeal and inadequate. So there remains questions around which buildings to target and what technologies to use when doing so. Energy benchmarking can be useful in identifying the poorly performing buildings and setting the targets, but it doesn't necessarily indicate the best strategies with which to improve the stock. So when retrofit strategy is done, it's likely to be based on case study findings. So these could be case studies where they've measured the performance of a building before and after a retrofit and reported the performance improvements and the effects on the quantities of interest. But these findings are quite difficult to generalize because there are physical building characteristics, as well as how the buildings are used and the system interactions, meaning that what works for one building may not necessarily be as effective when applied to another. And even if the findings from a case study could be useful to develop the strategy for one building, it's much more difficult when you consider that these parties have a very large and varied stock to deal with. But there's a growing recognition of the value of modeling, simulation, and data-driven approaches in retrofit decision-making. Here I'm talking about the physics-based energy models, which allow us to simulate existing and new buildings and output various quantities of interest. So with this, we can predict the performance of a retrofit before anything is altered in real life. And these have been used for many years. But in more recent years, we've been able to scale this approach up to the stock level and do urban building energy modeling. And this is primarily due to advancements in computing, but also because of improved availability and resolution of data. So this allows us to simulate a whole different levels of the stock, from a whole street, but all the way up to maybe a city or even a country scale, depending on the level of detail of the model and the purpose of the model too. And it also allows us to perform the analysis at these different levels as well. Also, doing stock level modeling allows us to capture some of the effects that wouldn't be possible when doing building level modeling, such as the energy transfers between the different modeled buildings, and also perhaps urban heat island effects and some microclimates. And we can also model entire thermal networks, for example, district heating or cooling networks, which would otherwise not be possible when modeling building by building. Now, I won't go into a lot of detail about the different types of UBEM. I'm calling them UBEMs, urban building energy models, because I think a previous webinar in this series went into quite a bit of detail on the types of UBEM. But what I will say here is that the bottom-up physics-based approach is the most common for retrofit analysis. And this is primarily because it allows us to quantify the impact of different technologies on the energy. And it can also capture the interactions between the retrofits. And also, as I've mentioned before, we can obtain the results at the building level if necessary as well, which aggregate up to the stock level. So these analyses can be done on two different scales. And these have no reliance on historic data. I'll talk about data on the next slide. But it's also worth mentioning the bottom-up statistical approach too, which can be used for retrofit analysis. And these can output similar things to the physics-based. However, they work slightly differently in that they rely on statistical analysis of historic data. So these can be more accurate for occupancy, but in general, they lack the predictive power of the physics-based models. And finally, top-down models are less able to represent impacts of specific technologies, but they can be quite powerful when used in conjunction with these bottom-up models, as they can be useful to understand correlations between aggregated demands and other variables such as fuel prices. So here are the general data requirements for physics-based urban building energy models. These are shown on the right-hand side. So this includes physical properties of the building itself and also geometry of surrounding buildings, but also information about how the building is used and the local weather patterns. And in general, some of these factors will be unknown and they'll need to be inferred or estimated from the data available and other research. And this may be a trivial point, but when doing retrofit analysis, you need to have a sufficient confidence in the current state of the stock that you're looking at. So if you don't have enough fabric or systems data for an accurate representation of the current state, it becomes quite difficult to perform a retrofit analysis. Now I'll give some examples of retrofit studies using UBEMs. So we have these different subcategories, and I've given examples for each of these. So we could map out decarbonization pathways, which the study has done here. And this is essentially mapping out roadmaps through time on how to decarbonize our stock. And UBEMs are suited to this because we can simulate the changing technologies with time, but also we can predict the CO2 emissions associated with each pathway. With the inclusion of cost data, we can also determine cost efficacy against other factors and possibly even cost these pathways and do an analysis of cost versus the performance of a retrofit, for example. So that's what this next subcategory represents. And combining these two considerations, UBEMs can be quite well suited to evaluating different policy interventions. And I mentioned it quite a few times now, but because we can analyze both at the building level as well as the stock level, this is probably something you'd want to do when evaluating policy approaches, as not only would you be interested in the macroscopic effects of how, for example, energy use or CO2 emissions of the area are reduced, but you also want to ensure that at the household or the building level, the occupants are still satisfied in terms of those health and social factors. So these references here do this kind of approach, but also the reference 6 complements the building physics approach with forecasts related to fuel elasticity and carbon intensities. So I mentioned that combining with other models for a kind of hybrid approach can be quite powerful in extending the scope of what the study is doing. The next subcategory is to do some solar PV potential analysis. And for this, you'd probably need quite high resolution LiDAR data. So LiDAR data can be taken from a drone survey or an airplane flight and has very detailed geometry, what we call point cloud data of rooftops. And this is what this study has done, analyzing the rooftops in London and the potential for solar PV. And if you were looking at integration, you could also use a UBEM to model this within a power grid network and see the effects on the individual households and also on the grid. Staying on the grid topic, you can model demand side response, which by necessity has to be on a large scale. And you can ask questions such as how much can the peak load be reduced by, but also what would the load profiles look like after this has been done. You can model district thermal networks, and this might be to model meeting peak demand, but it also could be system sizing and accounting for energy transfer between the buildings and any system energy losses too. And the final example I've got here, and just to mention, this is a non-exhaustive list. This is just some examples I've brought to show what can be done for retrofit studies using UBEMs. But the final example I've got here is looking at overheating in future climate scenarios. So because the physics-based UBEMs allow us to understand buildings' energy use as a function of the weather, this can be quite powerful. So future climate scenarios have already been created by researchers. These are essentially weather files which intend to represent the possibilities of the future in the climate. So these range from the pessimistic scenario of most hot future to maybe the optimistic, which is least hot. And we can simulate these and identify the buildings which are most at risk of overheating and determine the best intervention strategies to mitigate this risk too. So these are some examples. I'll now talk about the modeling choices you may have to make when looking into these kind of studies. So I'll attempt to lay these out in terms of temporal and spatial resolution. So there's a choice to be made around both of these resolutions. And I've placed these types of studies in the 4 quadrants ranging from, if I just bring my point here, ranging from low temporal resolution to high, and the same with spatial from low to high. So these may not necessarily be the case for every study doing this kind of analysis, but this is just intended to give an idea of what modeling decisions you'd need to make if you were approaching this kind of problem. So if I first look at temporal resolution, so a higher temporal resolution essentially means that the model generates more frequent outputs. So this would be important for anything where the variation in outputs is important on shorter timescales. So for power systems integration and for demand side response, you'd be interested likely in the profiles at a sub-hourly level, because these peaks and troughs can occur, at sub-hourly level. And so modeling at higher temporal resolution will probably be necessary for this kind of thing. However, if you're only interested in the annual outputs and you're looking at very large timescales and maybe looking at decarbonization pathways or policy interventions, you're probably not interested in a very granular approach with regards to time and future climate scenarios too. So these could be lower temporal resolution. And by reducing the temporal resolution, you also allow the model to simulate in a shorter time span. So this is one of the decisions you'd have to make. You'd balance the purpose of the model, but also with the computational expense and time that you have available. If we look at now spatial resolution, I've kind of put these 5 categories of studies on the low end and these 2 maybe in the high end. The main spatial resolution consideration you have at the urban scale is whether to use archetypes or not. So an archetype is intended as an average representation of a group of buildings classed by properties such as age and the fabric and use type. And this is a solution to both lack of data, but also the computational expense required to simulate such a large scale of buildings. So we essentially use one model to represent a number of buildings. And if you can imagine, this reduces some of the sensitivity to the orientation of the building, but also the surrounding context and the building specific geometry. So here we're using one house model and we're multiplying this out 4 times to get the aggregated results to represent 4 houses. But in reality, your stock might look something like this on the bottom. So you have a range of orientations and surrounding context. But this doesn't necessarily mean that it's a bad choice. So this is a common technique that's been applied to many UBEMs with a lot of success, and maybe a good choice depending on what exactly you're looking into in the study. So if I go back to this graph here, if you're looking at evaluating decarbonization pathways or the potential for a large-scale retrofit program, then archetypes could be quite a good choice for this. However, if you're looking into, for example, the solar PV potential or the future climate scenarios where you're trying to identify specific houses in the stock which would be at risk to overheating, then archetypes are probably not going to be the choice that you want to make, since these 2 studies would be sensitive to those factors. So they'd both be sensitive to building specific geometry. They'd be sensitive to the building orientation and also the surrounding context. So the shading would make a big impact for both of these 2. So these are just some choices you have to make as a modeler when doing this kind of investigation. So we've seen that urban building energy models can be very powerful, but the use of them alone doesn't necessarily ensure that we're considering the optimal solutions. So you can see we have quite a large number of possible retrofit options to consider, and we have a very large number of buildings usually to consider when we're doing stock level analysis. We also have a number of criteria to balance. These could be the environmental, health and social and so on factors that we've talked about earlier. So this frames as a multi-objective optimization problem. And I'll just give a fairly simple example of what this actually means. So here's a fairly simple optimization problem. You may have on the left, so you may have these retrofits that you're considering. You might have 6 different wall insulation thicknesses available to you. The same for roof. You might have 4 different window replacement options that you're considering, and so on. You can feed these into an energy model, and the model can give out these outputs that you may be interested in. Here I've just gone, for example, with annual energy demand and investment cost, both of which we'd want to minimize. And you might also want to place a constraint or a limit on the CO2 emissions. So this is an optimization problem in that on the right-hand side, we want to fulfill these criteria, which we call optimization objectives and constraints, by varying the things on the left, which we call the optimization parameters. And a simple way to do this would be to just simulate every permutation. However, this would result in almost 2,000 simulations. And what we normally do in optimization is apply an algorithm. So applying an optimization algorithm allows us to not the algorithm looks for optimal solutions without simulating the entire search space. So in this simple example, we could probably get away with 200 solutions or so. So 200 simulations, sorry. And the results from an optimization like this may look something like this. So here I've plotted, and this is just an example, these are not real results, but I've plotted the 2 optimization objectives on each of the axes of this graph. And each of these points just represents a different retrofit configuration. So each of these configurations have associated with them a different value for the energy demand and the investment cost. And what you can see, if you remember, we want to minimize both of these objectives. So the ideal point in the graph to be would be this corner. However, none of the points are in this corner because these objectives are conflicting. And in optimization, this is often the case. The objectives conflict one another, meaning getting to this corner of the graph is physically impossible. So what we then realize is that the best points available to us are these highlighted in red, which we call the Pareto from. It shows there's not one single optimal solution, but rather a range. And all of these points are of equal importance in terms of the chosen optimization objectives. So optimization is a common technique at the building level. It's been quite widely applied at the building level for retrofit studies. In fact, this literature review gives a good overview on many studies doing exactly this and applying it on existing buildings. And the most common choice of optimization algorithm has been the genetic algorithm, which is a good choice as it requires no prior knowledge of the nature of the problem, and they don't make any assumptions on the underlying landscape of the function itself, which is useful to us because in this kind of problem, we normally have no idea on what this function actually looks like. They also introduce an element of stochasticity, which helps to avoid local minima, which can be a common problem in optimization, not just in the buildings field. However, this level of research is not the case at the stock level. So there are a distinct lack of stock level optimization approaches, and those which do attempt it generally look at less than 5 buildings or archetypes. But Kali et al. Have noted that there's a necessity to develop this approach as it has significant applications in real-world scenarios. For example, with assisting organizations to effectively allocate a limited budget and resources amongst different buildings in the stock. And also the IEA say that organizing renovations on a multi-building scale can ease coordination among multiple stakeholders and speed up the process while reducing costs too. And in general, the traditional approach, which doesn't involve optimization, can be quite limited in that they usually employ techniques which only allow the investigation of a small number of options, and they're likely to also only focus on one factor, for example, energy savings or CO2 or factors related to cost. So we can see by now this doesn't necessarily consider the other important aspects that the decision maker has to balance. So you may be wondering what actually is the difference between individual building optimization and stock level. Why can't we just optimize each building separately? There are at least two reasons why we can't do this. One of them is the energy flows between the buildings. So if we want to account for these, we can't split these up and we must simulate these together. Therefore, we must optimize these together. But another reason might be that we might want to consider shared parameters. Now I'll explain what this means in the next few slides. But just to mention, there's an extra layer of complexity when you're dealing with the stock level. This is caused directly by the fact that you're considering many buildings at once. And shared parameters is one way I'm proposing to deal with one aspect of that complexity. My research aims to demonstrate that the manner in which the optimization problem is set up should be determined by the real-world problem that needs to be solved, as well as any real-world constraints and the desires for the format of the results as well. So I'll give a little example of the shared parameters and what effect this can have. So to set up shared parameters, we'd form building groups, and each group is given their own set of parameters. So we do this because buildings within a group will then receive the same retrofit recommendations in the results. And this can be useful, for example, for generating standardized retrofit packages. So a local authority may find it easier to group a number of buildings and develop a standardized retrofit package they can apply to all of these buildings for reasons of supply chain or delivery at scale. And it could also be useful in treating buildings of a similar property, for example, construction. If you want to give, for example, cavity wall dwellings all of the same retrofit package, then you can group these by this property too. So if we look at how this affects the results, here we have 3 different scenarios. This is a map of buildings 3 times. So these are the same area of buildings, but in 3 different scenarios. In scenario 1, there are no groups. In scenario 2, we've grouped by dwelling type. And in scenario 3, we've grouped, meaning that all dwellings are in one single unit. And if you remember, the effect of shared parameters means that dwellings within a given group receive the same retrofit recommendations. So these colors are showing, and this is one example simulation I'd done before, looking into the optimal roof insulation thickness for each of these dwellings. In scenario 1, you can see that each dwelling has received its own recommendation because there are no shared parameters. In scenario 2, we have the terraced houses here and here receiving a given recommendation. We have the semi-detached receiving a different one, and the detached receiving a different recommendation. And in scenario 3, all of the dwellings have received the same recommendation. So one of the key recommendations from the retrofit for the future project with regards to delivering at scale is to insulate adjoining houses at the same time. So with this kind of shared parameter approach, you can factor in the real world requirements or constraints and dictate what form the results should be in. So this is what I was talking about, where the real world considerations should influence how exactly the optimization is set up. And in the optimization, we'll find the best strategies given these constraints that have been applied beforehand. A bit more on how this affects the results. So another consequence of using shared parameters is that you reduce the overall number of parameters. And this can have benefits for the optimization algorithm, actually. So one of the challenges at the stock level is that there will be a very high number of parameters because you're considering so many buildings. So sharing parameters can actually improve the quality of results. You can see here in scenario 1, where we had lots of parameters, it's explored quite a small area of output space. However, in scenario 2, when we've reduced these number of parameters, the diversity of solutions has been improved by quite a bit. And in scenario 3, there are so few possible permutations that it seems to have just explored the entire parameter space. There are still a number of challenges to address when doing stock level optimization. And one of the main ones is the computational expense, because stock level modeling is already quite a computationally heavy task, and applying optimization on this can be even more difficult because optimization requires you to run the model hundreds or thousands of times. So some form of model simplification and optimizing of the actual energy simulation itself can help massively with this. I've already kind of discussed quality of results. So convergence of the algorithm refers to how its ability to find this Pareto front. And sometimes when there are loads of parameters, it can struggle to find a nice Pareto front. But on the flip side, sometimes it will converge too early. And this is what we're seeing here, where it's converged on this small area, meaning that the diversity of solutions is not very good. The genetic algorithms is still a good choice for the stock level, but it just needs more attention on how this problem is set up. So my recent research has been looking at how we can reduce the parameter space even further by, for example, only considering the buildings that need to be optimized together and splitting these up into smaller optimizations. Another one of the challenges at the stock level is analyzing and visualizing results. So because the Pareto front is composed of many solutions of equal importance, it's insufficient to focus on just one of these points. However, on the other hand, it's also impossible to perform an in-depth analysis on every single result here. There has been work on ranking the Pareto front, but there is an added dimension of complexity at the stock level where there's likely to be a set of results for every building in the stock. So if I just take a step back from optimization and talk a bit more generally about the challenges of applying UBEMs for retrofit analysis. One of the biggest ones is always data. In the absence of good buildings data, it can become difficult, if not impossible, to create a UBEM with any confidence. And this might extend beyond just buildings data itself, but might also be, for example, obtaining up-to-date cost data, if that's the kind of study that isn't in need to be undertaken. Also, the dynamic nature of urban environments can pose a problem, since the ownership, the occupants, and the building usage is always changing. So we can use historic metadata, this can be electricity or gas data, to calibrate models, but this doesn't necessarily give us an indication of future trends, since, as I mentioned, the occupants and the ownership are changing on relatively short timescales. So this can pose a problem too. On the other side of the data problem, it's also necessary to draw a line when modeling. So throwing more and more data at a model doesn't necessarily guarantee an improvement in accuracy. And actually, in some cases, you can see this negatively impacting the results too. The difficulty here is that there's no clear line, and this is very much case dependent and has to be decided on a model by model basis where this line lies. I mentioned occupancy data is very difficult. This is mainly because of their heterogeneity in behaviors. There are diverse populations to represent with varying demographics and preferences. And these demographics and preferences shape their needs and their comfort requirements, which in turn affect the energy use of the buildings. So far, occupants have often been represented as deterministic average heat sources, but recent research has shown it's probably not the best way to do things, and stochastic modeling of occupancy patterns is an active area of research. And this is an important area to address because occupancy is one of the biggest sources of uncertainty when doing urban scale modeling. And finally, urban scale so because stock modeling is a relatively young area of research itself, urban scale calibration techniques are also constantly being developed. And the next seminar will be talking about urban scale energy calibration techniques. So if you're interested in that, check out the next webinar in this series. And just some final remarks looking forward. So data, I mentioned, is a big problem, but aggregation and sharing could help with this immediately. So data sharing amongst private organizations, government bodies, and utilities companies could improve the availability, the coverage, and the quality of data. And sometimes, even if the data exists, it may be inaccessible to the researchers, or it may be scattered in a number of different sources. And this makes it quite difficult to match building to building. Reporting of model accuracy is very important, and having uncertainties in a model is certainly not a sign of poor research methods. It's rather an inevitable consequence of us trying to model the world around us. So reporting uncertainties in a transparent manner is important for understanding the implications of reported results. Also, with modeling tools, licensing fees can be prohibitive for many researchers around the world. So it's important that all communities have access to these tools, and that these licensing fees are not prohibitive for this research to be done globally. And finally, this slightly more specific of a point, but most of the software used for urban scale building energy modeling was created with individual buildings in mind, which means that it can be quite difficult when doing stock level analysis to interact with these models. They're not necessarily optimized to handle the stock, especially with regards to user interaction. So applying retrofits, for example, at the stock level can be quite a tedious task and can require knowledge of coding or programming in order to achieve what needs to be done. So seeing these become more friendly to urban scale studies in the future would be really useful to permit studies like this from to look into stock level analysis. So that's pretty much everything I had to cover today. Thank you so much for listening and for joining. And I've left my email here, so if you think of any questions afterwards, you feel free to drop me an email. But yeah, also feel free to send some questions into the Q&A box. And thanks very much.
Thank you, Shyam. That was great. A real thorough tour of UBEMS. We've got one question at the moment in the question and answer, which is, can you please suggest some of the softwares that can be used for stock analysis? One I know of is City BES, based out of LBL. Would you like to answer that? I can give you a paper suggestion as well, which might be quite useful.
Yeah, sure. Oh, sorry, were you going to say
No,
something
no,
else?
that's fine. If you keep going.
So yeah, as I mentioned, as far as I'm aware, there isn't some software that was specifically built for the stock levels. So often the underlying simulation engine is one that was designed for individual buildings. So for example, Energy Plus is a very commonly used simulation engine and is the one that is often used for the dynamic thermal calculations. Often what people do is build an interface on top of this in order to handle the stock level. So I think some of those stock level approaches essentially build a kind of interaction layer between the user and the simulation software to not only create these models, but interact with them and edit them. So yeah, I use Energy Plus, but we also use at UCL we have a tool called SimStock, which allows us to generate models on a large scale, and these simulations underlying also use Energy Plus.
Yeah, thank you. The paper that I was going to recommend is a paper by Martina Ferrando et al., and that is a state-of-the-art review of bottom-up physics-based approaches. It is often the case, always the case really, that you do need to look at the particular use case that you have and be very clear what you're trying to do when you choose the tool for the job. So there isn't necessarily a one-size-fits-all solution, but the paper is a very good overview of different options that you could use. So I'll pop that in the chat in a second. Another question for you, Shyam, is have you used Urban Opt and what are the benefits of using it?
I personally haven't ever used Urban Opt, no. So I unfortunately can't give too much comment on that. Yeah,
That's fine.
Sorry.
That's fine. You can't use all of it.
I don't want to say anything that's incorrect about it, so I'll choose to say not too much because yeah, I unfortunately have never used that myself.
Yeah, no, that's absolutely fine. So the next question is how do you determine the grouping of homes for optimization in the method that you've been talking about?
Yeah, sure. So the grouping is kind of determined by the problem at hand, and there's no predefined grouping that has to be used. So in the example I gave, in fact, if I maybe go back to that slide, here I've grouped by dwelling type. This may just be because you see similar characteristics across the dwellings. So terraced houses that are attached in a line like this may have similar properties, may be made of similar building fabrics, maybe of similar ages. So if this was a group of buildings you thought was suitable to treat in a similar approach, then you can group these. But the grouping is not predetermined. So you could also group by properties such as age, and these buildings may not necessarily exist together side by side. But if you group by age, then you would end up giving a certain age group of buildings a certain retrofit approach. So I suppose the answer to your question is you first have to determine what the real world problem is and what the constraints are in terms of how you're going to manage the implementation and the delivery of the retrofit, and what resources you have available to you, and what your stock looks like. And then you can maybe determine a suitable grouping method in order to develop these standardized retrofit packages. I hope that makes sense.
Thank you. That was perfect. I noticed a few minutes ago, someone raised their hand. I'm afraid we don't have the facility to bring participants in with audio. So if you were raising your hand because you had a question that you wanted to ask, then please do pop that question into the chat, into the Q&A, sorry, not the chat. There's another question here, which is for the non-domestic heritage building. Each building is unique. Do you think stock level approaches are still appropriate for this type of building?
Yeah, I think the uniqueness of each building doesn't necessarily prohibit you from using stock level approaches. So when you do stock level modeling and stock level optimization, it will take into account the characteristics of each individual building, and the results will reflect those individual building characteristics. Now, you may choose to group differently. So in this case, you might not group all heritage buildings in the way I've talked about for shared parameters, because this will obviously give all of those buildings the same retrofit. But if you're just doing a stock level, either modeling task or a stock level optimization, and you have the adequate data to capture the actual distinct characteristics of each of these buildings in the stock, then the results will most definitely take into account these individual characteristics. So I think the stock level approach is suitable for that kind of thing too.
Thanks, Shyam. The next question is, would the challenges in optimizing retrofit strategies be similar for commercial, residential, and mixed buildings?
Yeah, that's a interesting question. So my main focus has been on the residential stock for my study, but I understand that I suppose the main thing that I can see in the difference between the residential and commercial stock is maybe that you have even more variation in the commercial stock. So in residential areas, you can somewhat see some kind of similarities between the buildings, and in certain areas maybe that were built in similar periods in history. So you can see some kind of similarities, whereas maybe the commercial stock has a lot more variation. This could be a challenge. It kind of links to the answer I just gave, where you can still take into account those individual characteristics of the commercial stock if you were to apply this to the commercial stock. But maybe the difficulty there would be, how exactly do you represent these characteristics, and is it being captured in your model? Mixed buildings, I suppose, are also much more difficult, because then you have the question of who is in charge of the retrofit, and maybe considerations like that to consider too. So maybe it's not so straightforward in the actual implementation.
Thank you. I think that's a really important point, but also just about the way that studies have tended to focus on either domestic or, less commonly, non-domestic buildings, and the potential for approaches like this to look at optimization across the whole stock means that you can take factors like the type of building into account in deciding the best approaches in particular areas, which is great. So I think we've got 2 more questions for you, Shyam, and just a few minutes left. So we have the first question is, in this method, can you import the urban heat island effect on energy analysis?
By in this method, I'm guessing you mean stock level or urban building energy modeling. And I believe this is something you can capture. So you can capture, you may have to use it with Energy Plus, you may have to use an external calculation method. I've never personally looked into modeling the urban heat island effect, but it is something that I've seen studies do. I'm not exactly sure how you do this in terms of the actual technical implementation, but I know it's something that is possible.
Thank you. And then the last question is about how you might be able to use the stock level approaches and potentially optimization at the stock level for district energy considerations.
Yeah, that's a good question. So you can, as I've mentioned, with stock level modeling, you can model a district thermal network amongst the houses too. And if you've captured the houses on that network, you can model this whole thermal network. If you wanted to look at optimizing the network itself, this is definitely something that's possible, as the model would be able to output the quantities, the flow temperatures, the heat losses and things like this that you might be interested in optimizing. So you can set these up as parameters in your optimization. So yeah, district energy can definitely be something implemented in both stock level modeling, but also stock optimization. If it just really depends on what the question you wanted to answer is. I'll just leave my email up.
Thank you.
Oh, okay.
Yeah,
No,
you can pop your email in the chat. That would be great. So that brings us to the end of the questions, I think. So what I wanted to do now was to remind you that we have a YouTube channel where the recording of this session will be posted, and the sessions that we have had previously are all there, previous series as well. So do have a look at that. There's 41, probably 42 videos on there now, all of which are very relevant to building performance simulation, both at the individual building scale and at the urban scale. We've got 2 seminars coming up in this series, one in September, which, as Shyam mentioned, is Aisha Demir talking about the impact of spatiotemporal resolution on calibration of urban energy models. And then in November, we have Jianxing Hong from LBNL talking about the opportunities and challenges for urban scale building energy modelling. We are going to have some other seminars as well, so do watch this space for some new ones that we're going to announce. But I would also like to ask you, if you wouldn't mind just giving us a little bit of feedback. So firstly, which seminar topics have you found most interesting? So this is on Mentimeter again, and you can see the code at the top. So I think we probably have 2 minutes left to the end of this session. So if you've got time to let us know which of the urban building energy modelling and all the other seminars, in fact, that you've found, that you've participated in, you've found most interesting, that's really very helpful for us in planning future sessions. So I think a big thumbs up for you, Shyam, with the UBEM special topics there. I'll move on to the next question, which is my last one, which is what topics would you like us to cover in future seminars? So this is your chance to tell us what you would like to see in the future. So please do make the most of this opportunity. Great. Thank you very much for those responses. Do feel free to email in after this or connect with me on LinkedIn and let me know if there are others that you would like to see added. So then finally, I would just like to leave you with a plug for joining IBIPSA as a supporting member. So supporting members are able to for a very small fee, which has remained unchanged for a very long time, have online access to the journal and also to have a print subscription, as well as the warm glow of satisfaction that comes from knowing that you're supporting the good work of IBIPSA in the building performance simulation community. So do please find out more at ibipsa.org/membership. But I think that's all we have time for now. So thank you very much to Shyam for that excellent and very informative presentation. And thank you to our audience for all of your very interesting questions and the feedback as well, which is really helpful. And to Maya for her excellent technical support. So we'll just close it there. Thank you.
Thank you.